Hello everybody, welcome to part 3 of our series. If you remember part 1, I had told you that machine learning is subset of artificial intelligence, that is AI. Now to understand machine learning further, we will first need to understand what is deep learning. So deep learning is also a subset of machine learning and it talks about neural networks, what are they and how do they work. And this is the topic of today's video. So without wasting time, let's get started. So here as you can see, this is a diagram of the most basic neural network to exist in this world. This neural network is called as ANN, Artificial Neural Network. First of all, what is a neural network? So, as simple as its name, neural network is a network of neurons. So, in this diagram, as you can see, this is a neuron, this is a neuron, and all these circles represent a neuron. So now let us understand what are these neurons. So speaking mathematically, neuron can be imagined as a bunch of functions which act on certain input and they give some output. So this is what a model does. The contents of the model that I told you before, which are square, circle, triangle and all those stuff, are nothing but these neural networks. So we give input to these neural networks and then these neural networks perform a bunch of complex calculations, mathematical functions on the given input and they provide us some output. So now let us dive further and see what are actually these mathematical calculations that are being performed. So as I told you before, this is artificial neural network, ANN. So this is the most basic neural network available in the world and all other neural networks are developed from this neural network. By the way, a fun fact is that these neural networks are inspired from the neurons in our brain, the network that they form and how they work. So now let us understand how a basic neural network works. So as you can see here, this is called as the input layer. So basically in a neural network, layer is a collection of neurons. So this is our input layer and this is the output layer. So whatever information that we feed to our model first goes through the input layer of the neural network and then whatever the model predicts comes out of the output layer of the neural network. So now as you can see here in this example, the input layer has 3 neurons and the output layer has 2 neurons. So all the layers in between the input layer and the output layer are called as the hidden layers. So these hidden layers are the main part of the neural network that find out the complex patterns or sequences from the data and then predict the output. So now let us understand what actually happens inside a specific neuron. So this is, as I told you before, all neurons are nothing but a bunch of mathematical calculations that are being performed on the input. So now let us say that this is the input denoted by x1, x2 and xm. So like this is the first input, this is the second input and then we can have m number of such inputs. So for every such input we have a weight. So now these weights are nothing but constants. So for each input a weight will be assigned. So for x1 there is weight w1, for x2 there is weight w2 and for x3 there is weight wm. So this is the neuron. A neuron has input, a weight and also a bias. So now each weight will be multiplied with its corresponding input and then the sum of such input and weights will be added to the bias. Now as a matter of fact, these weights and bias are completely random and as we start training this neural network to predict something, these are just random values and the neural network keeps on tweaking these values until we get the output that we want. So it changes these weights and bias accordingly. So as to match the output. So this is what actually happens inside a neuron. However, you must have noticed one thing that this function here is completely linear. So we don't have a tool to predict the stuff that is non-linear. So like in our case, we are trying to build a model that predicts Bitcoin prices. So if you see the graph of a Bitcoin closing price chart, it may not be like a straight line like this or a straight line like this. It is always like something up and down, up and down. So it is basically a non-linear graph. So now we can't predict the non-linearity with a linear function. So to do this, we add another function to the final output of this function. So this function is known as activation function. So it is known as activation function. So what this function does is it adds a sort of non-linearity to the output. So this function decides that the output given by a specific neuron, that is the output given by by this function of a specific neuron, should be considered or not. So there are different types of activation functions, like there is sigmoid, which is the most basic activation function. Then there is ReLU. ReLU stands for rectified linear unit. Then there is ELU, which stands for exponential linear unit. So now if we try to again understand what happens inside a neuron is, okay, first let me erase this. So here is our activation function. Let us denote it by f of x. So this is our activation function. Now what happens? These are the inputs that are provided to a neuron. So basically, as I told you before, neuron is a function, a bunch of functions that are being performed. So these inputs will be multiplied by their corresponding weights. Then all the summation of these weights and inputs will be taken and added to a bias. Bias is yet another constant, just like weights. And then finally, the output of this function will be passed on to our activation function. So this activation function adds a sort of non-linearity in the output of this function, and it decides that whether the output provided by a neuron, that is whether the output provided by this function, should be considered or not. So this is what happens inside a very simple neuron. So now let us try to understand what are features. So features are the parameters that will be fed to our model or to our neural network, and the output that will be predicted by the neural network completely depends on the features that are fed to the model. So basically the features are the parameters on which the output actually depends in real life. So for example, in our project, we are trying to predict the closing prices of the Bitcoin. So if you have the basic knowledge about how the closing prices work, you must be knowing that at a specific timestamp, the closing price of the Bitcoin at that timestamp depends on open, low, and high, and also on the volume of people that are trading at that timestamp. So in our case, these are the features on which the closing price depends. So these features will be fed to the model. That is, the data of these features will be fed to the model. So a specific neuron has number of weights which are equal to the number of features. So like you can imagine that x1 is first feature, x2 is second feature, and like that we can have m number of features. So there will be m number of weights. However, a specific neuron always has one bias. So this is how the neuron works mathematically. So now let us go back to our diagram of basic neural network, that is ANN. So now as you can see here, these are the neurons, they are performing some functions and they are giving the output. So now let us try to understand the training process of a basic neural network. So here is a diagram of the training process of the neural network. So first we give input data to our neural network. Then this neural network tries to predict the output. However, as I told you before, the neural network cannot predict the exact output, and it gets closer to the output as the training process progresses. So here we have a method to compute the error between the output produced by the neural network and the actual output. These are again some mathematical functions, and the neural network provides the output, and this output is picked up by these mathematical functions, and they calculate error based on the actual output, that is the desired output that the neural network must be predicting. So now once we know the error, we can quantify how much deviated is the output produced by our neural network from the actual output. So once we know this, we now move forward to something called as backpropagation. So what happens actually during backpropagation is, here we have a neural network. So once it has given the output and we have calculated the error, we do backpropagation. So in this backpropagation, again there are some complex mathematical functions involved, and they calculate how much the weights and biases that I told you about before should be shifted from their current position. So like it calculates, okay, during this process the weight was this and the bias was this, so now it should be maybe added by, weight should be maybe added by 2, and this particular weight should be maybe subtracted by 2, and the bias should maybe multiplied by 5. So this was just the example of how it changes weights and bias, but it just keeps on doing this until it gets the desired output, or until it gets closer to the output. So this is backpropagation. We feed error to this backpropagation algorithm. It goes back to each and every neuron and then changes its weights and bias so as to match the desired output. So now once we are done with backpropagation, this is what I told you, that it changes the weights. It also changes the bias of each and every neuron present in the neural network. And this process continues on loop until it has gotten better and better at predicting the output. So now this complete process can be classified into three steps. The first step is called as forward pass. This includes feeding inputs to the neural network model, then calculate the predicting the output. The second step is called as loss calculation or error calculation. So as I told you before, the error computation happens here in the second step, and then is the third step where backpropagation takes place. This step is known as backward pass. So backward pass, and backpropagation and adjusting the weights and biases of the neural network model takes place in the backward pass. So these are the three steps in which the training process of a neural network model can be summarized. So another interesting thing to note here is, these weights and biases are initially just some random constants that a specific neuron chooses, and then during the backward pass, once the backpropagation is done, each neuron updates its weight and bias according to the error that we have calculated in the error computation process. So before that, the weights and biases are just completely random numbers which don't have any relation between them. Okay, now before moving further to our next type of neural network, let us first understand what is batch size. So as I told you, we have to feed the neural network some input data on basis of which it trains and then predicts the output. However, while feeding this data, we can't feed the entire data all at once, since now you must be knowing how much mathematical calculations are involved in all this process. Even the backpropagation algorithm and adjusting the weights involves complex mathematical functions and other calculations. So for that, we have to group the data and then send it in groups. So that is what is meant by batch size. So batch size is basically the number of data points that will be sent simultaneously. So if we specify the batch size to be, let's say, 40, then it means that the entire data will be sent in a group of 40 data points. So like the model will first receive 40 data points, then it will do all this process that I told you here. Then after this is done, it will take next 40 data points and then again repeat the process, and then again next 40 data points and then again repeat the process. So this goes on until the model has finished seeing all the training data. So this is what is meant by batch size. Now along with batch size, there is yet another concept to understand, which is epoch. So what are epochs? So epoch is basically the number of times the our model or our neural network sees the same data. So let us say that we have very big amount of data having many features, as in our case of predicting the closing prices. So for that, the model can't take out the patterns from the data or the important sequences from the data that are useful for predicting the output when it sees on the data only once. So what we have to do is we have to feed the data twice or maybe thrice to the model. So what we do is once we have fed all the data to the model, we again start from the first 40 group of data points and then again repeat the whole process, and thus we pass the same data through our neural network model maybe twice or maybe thrice. So if epoch is, let's say, 3, then our neural network model will see the same data for 3 times. Okay, so now once you have the knowledge about ANN, that is artificial neural network, we can now move on to slightly complex neural network, which is known as RNN or recurrent neural network. So this is how a recurrent neural network looks diagrammatically. By the way, the number of hidden layer a specific neural network has depends on the data that is being fed into the neural network. If the data is very complex or it is very long, generally the hidden layers or the number of hidden layer also increases. So it is not like this has 2 hidden layers and that has 1 hidden layer, so this is RNN and that was ANN. That is not the case. So what literally differentiates RNN and ANN is, in RNN, the neurons belonging to same layer have same weight and biases. So the weights and biases are shared among the neurons which belong to the same layer. Also, why are RNN used, or what is the use case of RNN? Let us understand that. So let us take a sentence. Let's say my name is. Now let us erase this is. And now if I ask you that what the word will be that comes after the name, you will definitely say that it is is. So this is what RNN is used for predicting. So RNN is specialized in finding out sequences and patterns that are not generally recognizable to human mind, and RNN helps us to understand these sequences and patterns from a large amount of data or maybe complex data, like in our case, which is predicting Bitcoin prices. So for in our case we are also using RNN, but we will not be actually using RNN. We will be using extended version of RNN, that is LSTM. I will explain about LSTM later on, but first let us understand what RNN is. So this was example of natural language processing, that is NLP. So definitely RNNs are used in NLP also. So now let us understand what are these arrows for. So if you see, these arrows kind of are like a loop. So they originate from the same neuron and end at the same neuron. So basically these represent that each neuron in an RNN stores some sequence. So as I told you before, here if we erase this is, we know that the next word will 99% will be is. So let us analyze that, how we know that. So what we did was we first analyzed that, okay, the first word is my, the second word is name. So the person who is saying this sentence wants to tell his name, and so definitely now he will use is. So this is what RNN does. It stores the sequence. So it will store, okay, the first word was my, the second word was name. Okay, so this is the sequence after which is comes. So RNN literally stores these sequences in mathematical form and then use these sequences while predicting the output. So that is why we are using this arrows. So now before going further, we will first have to understand another concept, which is time steps. So time steps is basically the number of data points that our neural network will analyze before giving the output. So time steps is the number of data points that the neural network requires to build a sequence which will be stored in the neurons of the neural network. So now before understanding further about time steps, first let us understand two concepts, that is how the data is fed to RNN model and what is the updated version of batch size with respect to a RNN model. So first of all, the data is fed to RNN model in form of some sequence. So what this basically means is that suppose we have 80 data points and the sequence is 20. So the data will be fed, like first 20 data points will be fed to the model simultaneously. then second 20 data points will fed to the model simultaneously, and so on and so forth. Now you must be thinking that this is similar to batch size, but that's why here the meaning of batch size is not really the same as it was before in the case of ANN. So here, what does batch size mean? So first let us assign batch size and time step some numbers. So let us say that batch size is 100 and time steps are 10. So now what does this mean? So if batch size is 100, it means that at the time we will feed our model 100 sequences, and these sequences will be 10 data points long. Now what does it really means is each group of data will have 100 sequences, and each sequence will be 10 data points long or 10 data rows long. So in a single group, there will be 100 sequences of data, and each sequence will have 10 rows of data. So batch size here doesn't actually mean the number of data points present in a single group. It instead means the number of sequences present in a single group of data that we are sending to the neural network. Now, if you remember, I had told you about the training process of the neural network, which has the following three steps, that is forward pass, loss calculation, and backward pass. So here in our RNN model, forward pass is when a sequence is passed for a forward pass, then we have loss calculation, and then we have the backward propagation and adjustment of weights and biases. However, this adjustment of weights and biases happens after each sequence of data points. So it doesn't actually happen after each data point is passed. It happens after each sequence of data point is passed. So the weights and biases will be updated after each sequence of data point passed, and until then those will be same across the neurons belonging to the same layer. Also, the backpropagation algorithm involved in RNN is not actually the standard backpropagation and the simpler backpropagation that we were using in ANN. Since this is a complex model, we need another backpropagation, and its name is BPTT, which means backpropagation through time. So this is what this is the backpropagation algorithm that we are using here. So what this does is it goes back, but it goes back in according to the each time step. So it doesn't actually go back according to each data point, it goes back according to each time step. Now let us understand how this BPTT algorithm is different from the standard backpropagation algorithm. So let's say that this is our RNN model, and what BPTT does is it will make a number of copies of this RNN model. So the number of copies made of this RNN model will be equal to the number of time steps. So since it is 10, we will have 10 copies of RNN model like this. So this is first, second, and we will have 10 copies like this, and each copy will represent the calculations that happen during each time step. So each copy will actually represent the calculations that happen during the processing of each data row or each data point. So this is T1, this is T2, and similarly we will have T10. So now these are symbolically connected to each other like this. So this will be connected to T3, this will be connected to T4, and so on and so forth until T10. So the meaning of connecting this to each other is this T1, T2, and T10 are actually treated like timestamps. So what happens during T1 is stored in this copy of RNN model. What happens during processing of T2 is stored in this copy of RNN model, and so on and so forth. So that is why the name of this model is backpropagation through time. And once it evaluates all these copies against the error it has received, then it is able to find out what will be better version of the weights and biases of the actual RNN model, and thus it now updates after evaluating all these copies, it updates the weights and biases of the actual RNN model. Okay, so now once we know the basics of RNN, let us dive deeper and understand how does it actually remember the sequence or the pattern from the data that we have fed into the model. So this is the diagram of how it actually works. So now let us understand what all these symbols mean first of all. So here X stands for input, Y stands for output, T stands for time steps, and H stands for hidden state, and all the other symbols which include W, they actually represent weight matrices, so weight matrix. So now now let me explain what are these words and what do they mean here. So if you see the diagram, this stands for the first time step. The part of this much part of the diagram stands for the first time step. This much part of the diagram stands for the time step before the first time step. So that's t minus 1. And this part of the diagram stands for the time step before this time step. So that's t minus 2. Okay, so let me clear this. So basically, this is the input at time step t, and this is the output for this time step, which is t, and this is something called as hidden state for time step t. Similarly, this is the input for time step before t, and hence it is represented by t1, t minus 1. Similar is the case with output and hidden state, and similarly, this is the input for time step before this time step, and similar cases with output and the hidden state. Now let us understand what is this hidden state. So hidden state can be imagined as a box which stores the pattern or the sequence that our RNN model has found out by processing the data that we have fed to it. So as you can see here from the diagram, this hidden state gets passed over from one time step to another time step to another time step. So the hidden state is actually passed over from time step to time step, and hence it influences the output that our model gives. So now if you remember here, what does this loop means? The information that the model finds out by itself is stored in this container called as hidden state, and it is actually passed over from one time step to the another during the process of training. So now let us understand what are these weight matrices. So if you see here, as I told you before, each neuron has some weight associated with it, and it is given to the input to perform certain mathematical calculations. So this is our weight matrix represented by WXH. This is our output matrix represented by WHY, and this is the hidden state matrix which is passed along with this hidden state to the next time step. So now if you wonder why do we need WHY, that is the output matrix, I hadn't told you about this in ANN. That's right, because in ANN we don't require this as we don't have any hidden state. So what does this hidden state does is it stores some vectors which represent mathematical vectors which represent the data that our RNN model has found out, that is the sequences and patterns from the training data that we have fed it. So this WHY weight matrix is required by hidden state to influence the output. As I told you before, this hidden state stores the patterns and sequences. So these patterns and sequences can be used to predict the output, and that's what this hidden state does. But while doing so, it requires this uh, output matrix which is known as WHY, and this matrix is required by hidden state to perform mathematical calculations on the output so as to influence the output. Now, what is this WHH? So, by passing the hidden state from the first time step to second time step, WHH is the weight matrix which is passed along the hidden state. In order to update or maybe to change the data that is stored in this hidden state, we require this WHS matrix, which is again helpful to perform certain mathematical calculations on the data which is stored in hidden state. So that's how our RNN model works at very minute level. So here we feed in the data, and and in this diagram, as you can see, this data is actually fed in the form of time steps, as I told you before while explaining the concept of batch size and time step. So this data goes in the model according to time step. Then for each time step there is a hidden state. This hidden state has some value, and it performs certain calculations on the output after the neuron has processed the output, so as to influence the output. So that is why RNN model can store certain information in this hidden state, and thus it is helpful for finding out sequences and patterns from the data given. So as to speak in layman's terms, actually our output is again fed into the neural network so as to find out the sequences and pattern and store them in the hidden state. However, if you go into the details, we are not actually feeding the output, but we are feeding the information stored in the hidden state along with the weights so as to update this information present in the hidden state. So that's all about RNN. So this was all about today's video. Today we have learned about how the neural networks actually work. Then we have learned about the two types of neural networks, that is ANN and RNN, artificial neural network and recurrent neural network. We understood that ANN covers the basics of neural networks, and it is the most basic or the most simple neural network present in the world. And for our purpose, we will use RNN, but not exactly or not directly. We will use the extended version of RNN. But for that, first we had to understand how RNN works, and for that we understood how this model works, what is hidden state and all that stuff. So thanks for watching. I will meet you again in the part 4.